Okay, section 4.4. It's time to solve quadratic equations by factoring. This is one of our algebraic or by hand techniques. So first of all, we're going to use a zero product property to solve equations, and we're going to factor by removing the greatest common factor. Then we're going to factor by trial and error. I'm also going to throw in the AC method, which is not in the book, but we'll do that too. It's not the same thing as trial and error. It's another method to use in place of the trial and error method if you choose. And then we're going to solve some quadratic equations by factoring. So all about factoring in this section. All right, so in the first example, we're talking about throwing our math book, oh my gosh, straight into the air. And the book's distance above the ground as a function of time is modeled by s equals negative 16t squared plus 16t plus 32. When the book strikes the ground, what is the value of s? So if the book is going to strike the ground, then the distance above the ground is going to be 0. So write the equation that you must solve to determine when the book strikes the ground. It's going to be 0 equals negative 16t squared plus 16t plus 32. Okay. I think we'll solve that question eventually. And then I guess if you're going to throw your math book into the air, you want to know how long you have to run away before it hits the ground. So we're going to solve this one eventually. The zero product principle or zero product property, we use those two words in this case interchangeably, the zero product principle or the zero product property, or the ZPP. This property says that if the product A times B is equal to 0, then either or both of A or B must be equal to 0. So A equals 0 and B equals 0. If either one of those is true, then this is going to be true, right? If either of those is true, then the product is going to be equal to 0. And there's no other way for the product to be 0 unless one of those is equal to 0. So if either one of those is true, if either is A is equal to 0 or B is equal to 0, then the equation becomes true. That's the zero product property. All right, so we're going to use that property to solve some of these already factored quadratic equations down at the bottom of the page. They've already been factored for us. We'll do the factoring on the next page when we get there. So the idea is that since this is already factored, this is a product. And this says 3x times x minus 2 is equal to 0. This is going to be true if the first part of the product, if 3x is equal to 0. It's also going to be true if x minus 2 is equal to b 0. And so the first one, if you divide both sides by 3, would give us x equals 0. The second one, if you add 2 to both sides, would give me x equals 2. So it doesn't matter which of those is true. If either one of those is true, if x equals 0, it's true, and if x equals negative 2, it's true. So we have two solutions to the equation by the zero product property. X is equal to 0 makes this true, and so does x equals 2. All right, so we solve again. Again, there's a product here. So if 2x minus 3 is equal to 0, this whole thing is true, and if x plus 2 is equal to 0, this whole thing is true. So if I solve this, these are both little linear terms, so I can add 3 to both sides. That's 2x equals 0. Divide by, sorry, that's 2x equals 3. And then I can divide both sides by 2. 0 plus 3 is 3. 2 divided by 2 is 1, so that's 1x equals 3 divided by 2. If you prefer to write that as 1.5, go ahead. Since it's not repeating, you can do the decimal if you want, or leave it as the fraction. So again, two answers. We'll have x equals 3 halves and x equals negative 2 for our two solutions. And the last one, again, it's a product, so x plus 2 equals 0 and x plus 3 equals 0. If I subtract 2 from both sides, that gives us x equals negative 2, or subtract 3 from both sides, that gives us x equals negative 3. And if either one of those is true, then the whole thing is true. So we have two solutions that could make this true. X is equal to negative 2 and x is equal to negative 3. Okay, so once they're factored, it's easy to solve them based on what I know about linear functions. You can add things, divide things to their side to get x by itself. The key is going to be getting them factored in the first place. So we want to rewrite the expression as a product by factoring. All right. The first type of factoring is removing a common factor. First, we want to identify the common factor, then apply the distributive property in reverse. So instead of multiplying, the distributive property would be multiplying both parts of the inside by 3. Instead, we're going to divide both parts by 3 and write the 3 outside. So we're undistributing. We're finding out what's in common in the two pieces to divide it out and write it in factored form. The largest piece that's in common is called the greatest common factor, or GCF. 3 was the GCF in this case because 3 and 6 can both be divided by 3, and that's the largest value that was in common. Okay, so onward, there's a couple more examples for you to check out, but onward, we're going to do some GCF factoring over here with number 4. First step is to find the GCF. The greatest common factor in the first one, 9 and 18 both have 9 in common, so the numeric portion of it's going to be 9. And then with the 8 of the 6th and the 8 of the 2nd, they both have at least 2 a's, so a squared is in common. So we're going to factor out 9a squared. When we factor it out, we write it outside the parentheses, and we divide it out of each term. 9 divided by 9 is 1, so I don't need to write the 1 because I'm going to have some a's in there. Took 2 of them out, so there should be 4 left. If I multiply those back together, I should get back to the 9a to the 6th. I am dividing the 9a squared out of the 9a to the 6th. 8 to the 6th divided by a squared is 8 to the 4th. That's what's left. Plus, then I have 18 divided by 9 is 2. And I removed all the a's already, so I have no a's left. And so that's factored by greatest common factor. So that would be our result for the first one. Let's do it again. In the next one, 21xy to the third, 7xy. The greatest common factor is going to have a numeric component. The number that goes into both 21 and 7 is 7. I have an x in both of them, and I have a single y in both of them. They both don't have more than one y, but they both have at least one y. So we're going to take 7xy out. When I divide that out, 21 divided by 7 would leave me with 3. X divided by x, there would be no x's left. Y to the third power divided by 1y would be y to the second power. Plus 7 divided by 7 is 1. Take the x out, take the y out, all I'm left with is the 1. So I do have to write the 1 here. I didn't write the 1 in front of a just because 1a absorbs the 1, but I have to write the 1 if it's the only number left. The plus can't be followed by nothing. There's got to be something here for us to multiply the 7 back by to get that term if I were to redistribute. So if I have 2 terms in the original expression, I should have 2 terms inside the parentheses to pair up with it when I go back. All right. 2 more. Let's look at the next one. We got to find the greatest common factor. 3, 21, and 33 for the number part. They have 3 in common, and they don't have any x's in common since the 33 does not have an x. So the only thing for the GCF here is 3. If I divide 3 out of the first term, I have just the x squared left, minus, I divide 3 out of 21, I have that minus 7 there. Keep the x because I'm not taking it out. And then 33 divided by 3 is 11. All I was able to do was to take out the 3 as the greatest common factor. You don't have to write down the GCF, but I think it helps to just see what it's going to be before we start pulling it out. And it does need to be part of your solution. So it's 3 times. It's not just the x squared minus 7x plus 11. It's 3 times x squared minus 7x minus 11 because this entire thing must be equal to the original. And the GCF needs to be multiplied by the parenthesis to make that happen. And last one, 4, 16, 24, you can divide 4 out of all of them, and they all have at least a singular x. So 4x is my greatest common factor. If I divide that out of the first term, 4 divided by 4 is 1. Take 1x out, I got 2 left. So I've got just 1x squared or x squared. 16 divided by 4 is 4. Took an x out, got 1 left. And minus 24 divided by 4 is 6. And I don't have any x's left because I took them all out. And again, we're done factoring those ones by greatest common factor. After we factor things by greatest common factor, we want to factor our trinomials into 2 parentheses. So the process is going to be by trial and error. So the way this works is if you take 2 parentheses and you multiply them together, like for example, x plus 3 times x plus 4, just for example. If you multiply those together, you know that you're getting your x squared plus your x times 4 is 4x plus your 3 times x is 3x plus your 4 times 3 is 12. And so you end up with x squared plus 7x plus 12. And so the idea for this is that the um, last term comes from the product of the two numbers in the last parts of the parentheses. And the first term comes from the product of the first two things in the parentheses. Then the other two terms are mix matched, and it's the sum of those mix matched things. The 7x comes from a combination of these mix matched products, the ones that are variable times constant and constant times variable. So we start focusing on the first term, the last term, because they have one route that they come from. And then we break down and try to get the middle two terms as the sum of those component pieces. All right. Now, they gave us 4 examples of the uh, uh, type 1 variety, because in the type 1 variety, the coefficient of x is 1, and it is in each of these. So we'll talk about these first, then we're going to go back and talk about it. Type 2, their example up here is in the type 2 variety, where the coefficient is not 1. The type 2 variety has a little bit more wiggle room, and we may have to try a few more times to get this one factored. So let's take a look at the first one. I know that the only way to make x squared is x times x. One choice and that's it. Now for 12, there are more options. 12 could be, let's see, it could be 2 times 6. It could be 3 times 4. It could be 1 times 12. So I want to think about all those possibilities. And then, if possible, we want to think about the pair that's going to add up to 7. So since this is just x, I don't have to worry about the interplay between the 1 and the 2 and the 1 and the 6, because 1 times 2 is 1, times 2 is 2, and 1 times 6 is 6. So this is the type 1, where I don't have to worry about this number of x's changing these numbers down here. So we can focus on just these numbers, and we want to find a pair that's going to add up to -7. So if I make these both negative, -3 and -4, -3 times -4 is going to be positive 12, and -3 plus -4 is going to be -7. So that's going to be the pair that's going to work to give us the sum of -7. So my solution needs to have an x in the first spot, -3, and an x and a -4. So that gets us factored. Okay, now if I look at the next one, again, because the first term is x squared, I don't have to worry too hard about the number changing the middle numbers. So I can work on really just the 49 right here, because the only way to make x squared is with x times x. So then I can work on 49. And I can say 49, that is 7 times 7, or 1 times 49, and those are my only options. And I need to add the middle terms up. And so the only way to make that 14 in the middle is with 7 plus 7. So this is going to factor into an x with a positive 7 and an x with a positive 7. Okay, so that's factored. All right, get to the next one. Again, x and x. The only way to make x squared is with x times x. So I got lucky again here that I don't have to worry about a number from the first term influencing the middle term. It's just the last number influencing the middle term. So now this is a -9. The final numbers for these two were positive, so I had to have them both being positive or both being negative. 2 negatives made a positive, 2 positives made a positive. Here it's going to be one of each. So I can have something like -3 times 3, or -9 times 1, or the reverse, 9 times -1. Now, the 8 that I want to create here is going to need to be a -8, so the 9 is going to have to be the -1, the 1 is going to have to be the positive 1, otherwise my 8 would have come out positive. So I know that I am at the x minus 9 times the x plus 1 case. All right, and the last one, the only way to make w squared is with w times w, and 25. I can make that with 5 and 5 or 1 and 25. Got to add 10, so 5 and 5 are going to do it. So that's going to be the correct pairing here. And so that technically the number goes first just because this is out of order. You could reorder it and then write the W first, but it doesn't really matter. So this is W plus 5 or 5 plus W. And I just realized that those are the same, and so were these. So I could have simplified this to x plus 7 squared and this one to 5 plus W squared because the two binomials are the same. Okay, so those are all type 1 factors where only the C term needed to be broken down to find the B term. That's not usually the case. It's only the case because every single one of these had coefficient A of 1. These all had A equals 1. So we're going to make ourselves a note in these examples that the way they work is all the same because A was equal to 1. Now we're going to look at this one right here, and A is not 1. Okay. Now, if A is not 1, the discussion would go a little different. All right. So I'm going to ignore the book discussion, and then we'll go back and look at it in a minute. I'm going to pretend it's not there and do my own. So I'm going to think about 6x squared. And I'm going to think, okay, well, 6x squared could be made from 2x and 3x, or it could be made from 6x and 1x. There's really not too many other possibilities for that, so I'm going to go with one of those possibilities. Then I'm going to go for the -3 and think, well, that could be -1 and 3, or that could be 1 and -3. There's no other possibilities. So I'm pretty lucky in the values here, 6 and 3, not having too many different ways to multiply to 6 or to multiply to 3. Okay, then I just start picking pairs, and I'm going to start with the first pair. Let's try to use the 2x and the 3x. So I'm going to try the 2x first and the 3x second. And let's go ahead and try, I'm looking at theirs right now to make sure I follow along. Let me try the 1 and the 3 first. So let's try the 1 and the -3, and let's just see, did it work? Okay, so let's try. We don't need to check the firsts and the lasts. We just need to check the two mixed products because those are the ones that need to sum to the middle term. So did we get there? So this would be 2 times -3, that's -6x, and this would be plus 3x, so that equals -3x. That is not what we wanted to get. We wanted to get -7x. So that means that this did not work. It was a good try, it just did not work. I wouldn't cross it off all the way. I want to see what I did. I just crossed off the light color so I could still see what it was, but it didn't work, so I'm going to try something else. Okay, so I tried the 2 and the 3 with the 1 and the -3. It didn't work, but I could try it again with the other order. So what if I paired the 2x up with the -3 and I paired the 3x up with the +1? Does it work in that order? Let's find out. Okay, check your mixed products here. 2x times 1, that's 2x, minus 3 times 3 is 9x. That gives me -7x. -7x is what we want. Remember, we want to get -7x there in the middle. So that means that this is the correct answer. So our answer here is 2x minus 3 times 3x plus 1. That is the correct pairing of binomials because it has the correct outer product, 6x squared, the correct inner mixed product of -7x, and the correct last product of the -3. So when a value is not 1, we have a lot more things to think about in terms of the product combining the first pieces and the last pieces using the trial and error method. All right. Now, there is a way to be more systematic about this. It's called the AC method instead. So I'm going to show that method real quick on just some other paper. And then you get to decide which method you like. So same question. It's still going to be 6x squared minus 7x minus 3. Just for fun, the AC method's going to start us off with a times c, which is negative 18. And we're going to use the negative 18 and break that up and try to get to negative 7 as a product. So we're going to think about things that go into negative 18. So for example, I could do 6 minus 3, because 6 times negative 3 is negative 18. And that would get me 3, and that does not work. And then I could try 9 and 2. I'm looking at my sign. I want this to be negative. So I'm going to try negative 9 and a positive 2 to get negative 7, and that would work. So those two numbers are not the answers, but they're the two numbers I would separate the middle term into. So I'm going to take my 6x squared, and instead of writing the minus 7x, I'm going to separate that into negative 9x plus 2x minus 3. So I'm creating four terms where there used to be 3 by separating this one into those two specific pull-out terms. Then we're going to GCF factor each of these two groups. So I'm going to GCF factor. The GCF of these is going to be 3x. And if I take 3 out of 6, I'm left with 2. I took 1x out, there's 1x left. Take 3 out of 9, I get negative 3, and no x is left. Okay, now these two terms don't have a GCF. Well, everything has a GCF. It's just there's nothing in common besides 1. 1 goes into 3, 1 goes into 2. Nothing else goes into both. So 1 is what we're going to take out. So we're going to take out 2x minus 3. We're going to have 2x minus 3 left, and we'll take 1 out. Now, what we say is that the 2x minus 3's is what's in common. So the 2x minus 3 comes out. And if you remove that, what's left is the 3x plus 1. So our solution from our AC method of factoring is the same thing as our solution from trial and error. 2x minus 3 times 3x plus 1. And again, this was a little bit more procedural, although the method is certainly different. You need to decide which method that you are the most comfortable with, and you need to practice that method. All right, so on to the solving quadratic equations by factoring. We're going to go back and solve the one in the beginning. The equation that we had at the beginning was 0 equals negative 16t squared plus 16t plus 32. That's coming over from number 2 on the first page. And I want to solve it by factoring. The very first step of any factoring is GCF. And these numbers have a GCF of 16 goes into all of them, and if the first term is negative, pull the negative. So I'm going to say the GCF is negative 16. I don't want to factor with a negative t squared because that would be the a not equals to 1 case, which is more challenging. So get rid of the negative while you're pulling out your GCF. So I'm going to take negative 16 out. That's going to leave me with t squared inside the parentheses. 16 divided by negative 16 is negative 1t. And 32 divided by negative 16 is negative 2. Now, because this is a t squared, the only way to make a t squared is a t and a t. So I can start factoring this into two parentheses where I have t in the first place in both of them, because that's the only way to make t squared is t and t. No choices to go through here. Then I need to take my negative 2 and I need to figure out how to add to negative 1. So I know that if I take 2 minus 1, that 2 times negative 1 would give me a negative 2, but 2 minus 1 is positive 1. So I've got to have 1 minus 2 to get the 1 negative, right? So the 1 has to be positive, the 2 has to be negative. So this is going to be t plus 1 and t minus 2. 1 times negative 2 is negative 2, and 1 minus 2 is negative 1. Perfect. So we are factored now. And then we're still trying to solve this. And so we're using the zero product property next. And the zero product property says take every factor that has a variable that has something to solve and set it equal to 0. The negative 16 does not have a variable. Negative 16 cannot be 0. But t plus 1 can be 0 and t minus 2 can be 0. If t minus t plus 1 is equal to 0, and I subtract 1 from both sides, that gives me t equals negative 1. And if t minus 2 equals 0, and I add t to both sides, that gives me t equals 2. So the answers, this was all supposed to be part of A, I just couldn't fit it in A. My answers are t equals negative 1 and t equals 2. All right, now, question B. Are the solutions, both of them, t equals 2 and t equals negative 1, also answers to the question, at what time does the book touch the ground? And so the first one is not, because it's not in the practical domain. Because the practical domain does not start until you drop the book, which was at t equals 0. So only the first one answers the question. So the book hits the ground after 2, is it seconds? I need to look back. Just as a function of time t, it doesn't give me units. Seconds, minutes, hours. I'm going to go with seconds likely. But we'll just say 2 units. This one's the solution. I'm going to guess seconds. Maybe the units are there somewhere and I just missed them. I don't know. We'll say 2 seconds, the book hits the ground. Okay. Now, 7a, new question, but related. Now we want to know at what time the book is 32 feet above the ground. Maybe there's a fence we're trying to chuck this book over. And so we're going to set this equation equal to 32 instead. So 32 equals our negative 16 t squared plus 16t plus 32. All right, onward. Solve the quadratic equation by factoring. So it's 32 equals negative 16t squared plus 16t plus 32. If I'm going to solve by factoring, I have got to get this equal to 0. So I have to subtract that 32 over to get this equal to 0. When I do that, that gives me a 0 equals negative 16t squared plus 16t plus 0, because it happens to cancel off, luckily enough. So I'm going to continue factoring, GCF style. The GCF is negative 16t this time, because they have both the negative 16 and the t in common. When you have a leading coefficient that's negative, you always pull the negative. So this is going to be negative 16t times just a t, and then 16 divided by negative 16 is negative 1. Then we apply the zero product property and pull this off to negative 16t. Since that one has a variable, I set negative 16t equals 0, and the other one, t minus 1 equals 0. If I divide both sides by negative 16, this one gives me t equals 0, and if I add 1 to both sides, this one gives me t equals 1. So this means that the book was at a height of 32 initially, and after 1 second. So if you checked it straight up, you better duck after 1 second so the book doesn't hit you in the head. Okay. So solve the next set of quadratic equations by factoring. All right. They gave me some a not equal to 1 scenarios. Awesome. So we're going to factor the first one, and I'm going to make some notes off to the side that we can make 2x squared with 2x and x. Luckily, there's only one possibility for that. 2x and x, or x and 2x, doesn't matter the order. So we're going to write that down here. And then we can make our negative 6 with a negative 3 and a 2, or vice versa, and a 6 and a negative 1, or vice versa. The signs can change on those. That's really 4 different pairs. I'm just going to write all 4 of them down. There's 4 pairs there. So we're going to start guessing. We're going to say, let's say the 2x and the x, let's say I pair those with the negative 3 and the positive 2. And again, I don't know immediately if this is going to work because it depends on the interplay between the mixed terms right here. So I got to find out if I did it right or not. So 2x times 2, that is 4x minus 3x. That's 1x. So I actually almost got it. I want it to have a -1 instead. So that means I got my signs wrong. So let's try the 2x with a +3, and let's try the x with a -2. So when we check the interplay there, this should show a -4x, and a +3x gives a -1x. And so that means that our answer here is going to be 2x. This is a solve situation. So hold on, I gotta do some more writing. That means that our answer is a 2x plus 3 times an x minus 2 equals 0. And then the factoring part of it is done, so we have to use the zero product property. And so we'll set the 2x plus 3 equal to 0, and we'll set x minus 2 equals 0, and then we will solve. So we're going to subtract 3 from both sides. That gives me 2x equals -3, divide by 2. The first one is x equals -3/2 for my solution, and then we'll add 2 to both sides. So that one gives me x equals +2. So my answers are x equals -3/2 and x equals 2. So I have got 2 answers to the first one. When A is not 1, they can take a while. There were 2 other possibilities I hadn't even tried here, and if one of those had tried, I would have had a couple more mistakes before I had found the correct answer. So this is the A not equal to 1 case. I'm not guaranteed to pick the right pairs on the first time, and that's okay. Just keep trying until you can verify that the sum of the mixed products is the thing that you want to have as your middle term. All right. Now, when I get to the next one, I notice that its A value is not 1 either, but unlike the first one, this one's a trinomial with A not equal to 1. So this is the process I use for my trinomials, A not equal to 1. Not a trinomial, just a binomial, so I just got to do GCF. There's not a third term. And there is, more importantly, something in common right here. So we're going to GCF this. And they can both be divided by 3 and x. So we're going to pull 3x out. That's going to leave us with x minus 2. And if I set each of those with a ZPP, a zero product principal, equal to 0, I can divide by 3, and I get x equals 0, and I can add 2, and I get x equals 2. So 2 answers to this one also. X is equal to 0, and x is equal to 2. And the last one, okay? They don't give me enough room for any of this stuff, but it's not equal to 0 yet, which is a problem. I cannot factor if I'm not equal to 0. So I'm going to have to add this x over and add the 6 over to move those two terms. So that's going to give me x squared plus 5x plus 6 equals 0. Luckily on this one, the a value is 1. It's a trinomial, but the a value is 1. And because the a value is 1, I know that when I factor this, that the only way to make x is x and x. So I don't have any options on that. And I just need to look at the last term. So 6. 2 and 3 make 6, and 2 and 3 make 5. And so that's the pair that we're going to need, right? 2 plus 3 is 5. So x plus 2 and x plus 3, this is equal to 0. So we can apply our ZPP. And this means that x plus 2 equals 0 and x plus 3 equals 0. So if I subtract 2 from both sides, x equals -2. And if I subtract 3 from both sides, x equals -3. So our two answers here are x equals -2 and x equals -3. And then determine the zeros of the function defined by 2x squared minus 3x plus 1. So this is just an in-words way of saying the same thing. Determine the zeros. They want me to find out when the equation is equal to 0. So we're going to get it factored first. This is an a equals not equal to 1 because a is 2 here. So we're going to go with our 2x squared. That's going to be 2x and x, or x and 2x. The order can change. And then our 1 for our C, we're doing the A term and the C term. And luckily 1 is just 1 times 1. Or it's actually, in this case, not just 1 times 1, because I can see the middle term is negative. I know already I want those to both be negative. Now, there are not very many possibilities here because these are the same number. I'm going to probably get it on my first try. So let's try it with 2x minus 1 and x minus 1. But I have to check to make sure that my mixed products are the correct number. So this is 2x times negative 1 is negative 2x minus x. That's negative 3x. And so we have the correct middle term. All right. So now we can move on and say that we're looking at 2x minus 1 times x minus 1 equals 0. And then the ZPP set each of these equal to 0. 2x minus 1 equals 0. X minus 1 equals 0. If I add 1 to both sides, 2x equals 1. Divide by 2. X equals 1 half. Add 1. X equals 1. So there are two solutions, x equals 1 half and x equals 1. And again, just noting all of this stuff was for number 8. Definitely didn't give me enough room on number 8, but I kind of squeezed the rest of them in. So there we go.